So then what you're going to do is take this, and because it's 1-to-1, meaning it's a monoprotic acid, we're going to get 1 H plus. We know that this is also equal to H plus. So to find the concentration of H plus, we would put that over the total moles, and we would get our molarity. So that's the concentration of H plus, negative log that to get the pH. And that's what we'd expect, because we would expect a strong acid to have a low pH between 1 and 2, and we're looking at strong acid. Now you can ignore any of the NH4 that contributes H plus, because the H plus contributed by a strong acid is going to so outweigh any contributed by a weak conjugate acid or weak acid. So we can just ignore that, it's negligible. So the last part of this video is going to be focused on graphing this. Okay, because you need to be able to do the calculations and then also graph them. Pretty straightforward. You just need to know the shape of titration. Graphing is just graphing. So before I do that, this is what I was talking about with the burette. So in the problem we just did, the calculations we did, we would have had a flask full of NH3, or a beaker in this case. And then you would have a burette with HI. And you turn this little knob, and you're going to do this in real life. You turn this little knob and you do drop by drop by drop until you get to the equivalence point. And then after, if you want to, keep doing the calculations. After, the way to see if you're at the equivalence point is going to be different ways. Okay, we have indicators, we have pH meters, we have all kinds of stuff that we'll talk about in the next video. So for right now, we're just going to do some titration stuff real quick and show you how to graph it. So for this first one, you're starting with a strong acid, 10 mils of a strong acid, and you're using a strong base as your titrant. So the pH value at the start, you can just take the concentration of the strong acid and negative log it. You would get 1. The volume needed to neutralize, is 10 mils because it's monoprotic acid and NaOH has 1 hydroxide per mole. The pH at the equivalence point is going to be 7 because it's strong acid and strong base. So remember, when strong acid reacts with strong base, it neutralizes to water, so it's going to be 7. The pH beyond the equivalence point will be a little less than 13. Okay, so let's take a look at our points. At 0, we have a pH of 1. At 10, we have a pH of 7. And after that, we'll have a pH right about here. Okay? So all of your titration curves are going to take the same general idea. They have a little bit of a flat part at the top. They have almost a vertical part around the equivalence point, and then another curve to the flat part. At the end. Well, that looks terrible. Let me try that one more time. I'm going to try it from the bottom. Because you need to have this vertical part. There we go. Okay, so that's what they should look like, something like that. For strong acid and strong base, it's pretty easy to do because we have pretty much the same. For the weak ones, we're going to have different Kas, so we're going to have different numbers, but we'll get to that in a minute. Before we do that, let's do it the other way around. For this one, you would be starting with NaOH, so that would be in here, and you're going to titrate it with HCl. So it's going to be the same idea, except you're going to start, the pH at the start is 0.1 OH. So you do that negative log and then 14 it. So you would get 13. The volume needed to neutralize is still 10. pH at the equivalence point is still going to be 7 because it's strong and strong. And it's going to be a little higher than 1 at the very end. So we would take 13. And then at 10, we're at 7. And then after 10, we're about 1, a little bit higher. Okay, so same thing. You have this weird little straight part, and then it goes straight down at the equivalence point and curves back out. Okay, so again, it will look something like that. So those are strong acid, strong base curves. They all pretty much look the same. They're all going to neutralize at 7 and all of that great stuff. Okay, so if you start with an acid and use a base, it looks like this. You start with a base and use an acid, it looks like this. So now let's take a strong, weak acid and a strong base. Okay, now I'm just going to give you the calculations, the answers to numbers 1 through 5. Okay, but you could do it the way we just did it. We went through, like, it would be the same exact calculations, and at the end they would say, okay, graph it. All right, so I'm just going to give you this. So 2.87 will be the start. The volume needed to neutralize is 10. Halfway to the equivalence point is 4.74. Whoops, that's 77. The pH at the equivalence point is greater than 7. And the pH beyond the equivalence point is going to be a little less than 13. Okay? So we are going to start with 0 at 2.87, so right about there. The half equivalence point, which is going to be 5 mils, is going to be 4.74, so right about there. At the equivalence point, it's a little higher than 7, so at 10, right there. And then after, we'll do a little less than 13. Okay, so again, you're going to, at the equivalence point, you're going to have a vertical part, and you're going to have this little curve, and then this curve up here. So it's going to look something like that, but you can see that it doesn't look quite the same as the one we just did. Okay, and the ones you're going to do in class, you'll actually find even more points to help you out. So it has the same basic idea, but they don't look as smooth and pretty as the strong and strong. Okay, so here is another one. This one is 10 of NH3 with 10 of HCl, 0.1 NH3, 0.1 HCl, excuse me. So this one you have the numbers here, and I just kind of left this a little bit better because now it's not me drawing it. So halfway to the equivalence point would be 5, and you can see that's right about 9.25. Okay? And then your equivalence point, they put it right there. So here are what the different things will look like. And I put this in your note as well. You can see the strong and strong are nice and easy to follow. You can see that the weak acid with strong base, it's still there. It's still the same basic shape, but it's going to have a much smaller incline. The sides are a little more curved, and the same with the weak base and strong acid. So now let's do some questions that would go with this. So the equivalence point of this titration occurs at what pH? So to find that, you would find about the midpoint of your vertical part. So I would say right about here, so right about 9. So you find the equivalence point by looking at your vertical, right about the middle of it. So for this one, oh, you know this. Halfway to equivalence point is the easiest way to determine Ka or Kb. You know that because H plus is equal to Ka. So pH is equal to pKa or pKb. And then here are some different Ka values. And you can, this is always the equivalence point, this vertical part, but you can see how the parts before them can vary. Strong acid doesn't, we don't really give Kas for strong acid, but they're pretty much just one. So they're going to be, that's going to be the biggest one. Okay, so questions. What is the Ka of this acid? We just said the easiest way to find the Ka is to find the half equivalence point. Okay, so if we have the equivalence point is right, let's say 14, 7, right about here, that would get your pH to 5. So I would say your equivalence point is 1 times 10 to the negative 5. So this question says, this is the titration curve of a blank with a blank, okay? You know it's some kind of acid because it starts below 7, okay? So anything that says base, you can get rid of right away. All right? Now we know it's not a strong acid because strong acid would be more around 1. So your last choices are weak acid with strong base or weak acid with strong acid. You don't titrate an acid with an acid. Okay, that's not what you do. If you did, why would it be going up? It would just kind of go like this. So that's not something you would do. So it's got to be a weak acid with a strong base. You also could look and say, okay, my equivalence point is at about 9. And we know that the equivalence point of a weak acid is going to be higher than 7, right? Because we said that's because of the conjugate base. So that's also how you could do it. So either by process of elimination or just looking at the equivalence point. So next one, what is the Ka of this acid? If we look at the equivalence point is at 25. So if we look at the half equivalence point, let's say right about here, 5.4, not quite 5.5, so 5.4. That would be the pKa. So the pH would be equal to the pKa. So that would be equal to 5.4. So to find the Ka, so the one that, so you know that if you look at the log rules that we talked about before, for this, we're going to need something between right around 4. So here we go. And if you did have a calculator, you could figure it out entirely, but if you didn't, you can just kind of estimate it. All right, so here, determine the molar mass of this acid. 0.76 grams of it was titrated with 0.15 moles. Okay, so what you can do is figure out the moles of acid at the equivalence point. Okay, so if we take this The mole, okay, so the equivalence point is about, what, 24 mils? Okay, so to find the moles of acid, or the moles of base, excuse me, we would do the molarity times the liters. You could do this in millimoles as well. And you would get this. Oh my goodness, that is Walter. No joke, that is what he sounds like. I have not been paying enough attention to him. So now we have the moles of the base. Oops. That's going to be the moles of the acid at the equivalence point as well, because we know moles of base equals moles of acid. So what you can do is take the grams, put it over the moles, and that will get the molar mass. So 0.76 comes out to around 200. All right, so for this weak base titration, the pH at position 2 is going to be at 7, below 7, above 7. Okay, so that's the equivalence point. And we know for a weak base titration, at the equivalence point, it's going to have an acidic pH, right? Because that conjugate acid. So weak base, adding a strong acid, we're going to have a conjugate acid at the equivalence point. So you know the conjugate acid tells you it is a pH above 7. Here, it's asking for position 1, which is the half equivalence point, but we would need to know the Kb, and we don't have the Kb here. So since we don't know the Kb, we have no way of knowing what that would be. And then last one, we looked at some of these already. This one says, which one represents the acid with the largest Ka? This is kind of a weird one because the red one is a strong acid. Look, it starts at 1. So technically the answer should be red, but we don't really think of strong acids having a Ka. So honestly, I would say 7 would be okay. Orange would be okay. But the real answer is you want to say red because we don't think of it as having a Ka, but the Ka is essentially 1. And all the other ones are going to be times 10 to the negative something. So we would say the red one. All right, so that's it for this video, for the titration video.